Hello everyone. Today we are going to discuss about some points of UV visible spectroscopy. So firstly, we will see the spectroscopy. Now we all know that spectroscopy is the combination of electromagnetic radiation and matter. It is divided into two types: atomic spectroscopy and molecular spectroscopy. In simple words, we can say that atomic spectroscopy is the interaction of electromagnetic radiation with atoms, and molecular spectroscopy is the interaction of electromagnetic radiation with molecules. Now let's see the principle of UV visible spectroscopy. We all know that UV visible spectroscopy is the absorption spectroscopy. So, in which light of ultraviolet region, which is ranges from 200 to 400, is absorbed by molecule, which result in the excitation of electron from ground state to higher energy excited state. According to MOT theory, when molecule absorb the radiation, its electron is promoted from bonding to antibonding orbitals. This is called electronic transition. Now, electronic transition is divided into three electrons: sigma electrons, pi electrons and n electrons. First, sigma electrons. Sigma electrons are involved the saturated sigma bonds. These are the lowest energy occupying molecular orbital, that is the sigma orbital or sigma bond. Second, pi electron. These are those electrons which involve unsaturated hydrocarbons. And third is the n electrons. These electrons are involve lone pairs or non-bonding orbital. They are also lie at the higher energy level. For example, nitrogen, oxygen, halogen.
So further, we will discuss about the electronic transition shifts. The energy required for various transition follows the order sigma sigma star, n sigma star, pi pi star and n pi star. First, sigma sigma star. These transitions can occur in such compounds in which all the electrons are involved with single bonds and there are no lone pair of electrons. Examples are saturated hydrocarbons and methane, which shows the wavelength of 125 nanometer. N sigma star. Saturated compounds with lone pair undergoes N sigma star transitions. In addition to sigma sigma star transitions, the heteroatoms like oxygen, nitrogen, sulfur will shows the N sigma star transitions. The wavelength is 150 to 250 nanometers. Pi pi star. The pi pi star transition corresponds to the promotion of an electron from a bonding pi orbital to an anti-bonding pi star orbital and are observed in compounds with unsaturated centers such as alkenes, carbonyl compounds and aromatics. Alkenes, alkynes and carbonyls are the examples of pi pi star transitions, and they generally absorb in the region of 170 to 205 nanometers. N pi star. N pi star transitions are shown by unsaturated molecules which contain heteroatoms such as oxygen, nitrogen or sulfur. N pi star transitions and electrons of unshared electron pair on an heteroatom is excited to pi star non-bonding orbital. So further, we will continue with chromophore, the group which exhibit absorption of electromagnetic radiation in a visible or ultraviolet region. These are the molecules or group of molecules which absorb the light in UV visible region and helps to impart the color into the compound. Examples: nitro group. When nitro group reacts with colorless benzene, it will give pale yellow color. Some of the other important chromophores are ethylene, acetylene, carbonyl, acids, esters and nitrile groups, etc. Types of chromophores. There are two types of chromophores: dependent chromophore, independent chromophore. Dependent chromophore. More than one chromophore is required to produce a color in compound. It's called as dependent chromophore. Examples are carbon with double bond O groups and carbon with double bond carbon groups, etc. Independent chromophores are a single chromophore which imparts a color to the compounds. Examples are azo groups or nitro groups. Further, we will discuss about the auxochromes. It is a group of atoms that get attached to the chromophores and increase the colorfulness of the chromophores, and it is also called as color enhancing groups. Examples are benzene and aniline. Benzene having the wavelength of 255 nanometer and aniline having the 280 nanometer. With the presence of NH2 group, it will enhance the wavelength of the molecules.
Spectral shift. It is defined as the difference between the frequency at which the spectrum takes its maximum and that of original spectrum. So what spectral shift says, the position of absorption maximum and absorption intensity can be modified in different ways by some structural changes or change in polarity of solvent. Generally, the spectral shift has a gradual change with same parameters. It involves following four types. First, bathochromic shift, which is also known as red shift. Second, hypsochromic shift, also known as blue shift. Third, hyperchromic shift, and fourth, hypochromic shift. So, we will see first bathochromic shift. It is an effect in which absorption maximum is shifted towards longer wavelength due to presence of an auxochrome or by the change of the polarity of solvent. So in bathochromic shift, the graphical view shows that the maximum is shifted towards the right side, that is longer wavelength. The example, the n-pi star transition for carbonyl compound experience bathochromic shift when the polarity of solvent decreases. Second, hypsochromic shift. It is an effect in which the absorption maximum is shifted towards shorter wavelength due to removal of conjugation or by the change of polarity of solvent. So in hypsochromic shift, the graphical view shows that the maxima is shifted towards left side, that is shorter wavelength. Hyperchromic shift. It is an effect in which the intensity of absorption maximum increases, that is the value of Emax increases. Example for it, increase in intensity of absorption of DNA due to denaturation at the lambda max 260 nanometer. Fourth, hypochromic shift. It is an effect in which the intensity of absorption maximum decreases, that is Emax decreases. Example, when a methyl group is introduced in position to biphenyl group, hypochromic effect occurs because of distortion caused by methyl group. Here is a spectral shift graph. Solvent effect on absorption spectra. The choice of solvent used in UV spectroscopy is most important because solvent can change the absorption maximum. So basically, the solvent used can be responsible for the spectral shifts we have seen before. A most suitable solvent is one that does not itself absorb radiation in the region. So the relation between polarity and wavelength of absorption maxima is given as polarity decreases, the absorption maximum, that is lambda max, increases. 90% ethanol is most commonly used solvent. The order of polarity of different solvents used in spectroscopy is given as the polarity of water is greater than methanol, greater than ethanol, and greater than benzene, and then hexane. From this relation, the absorption maxima of some solvents is given.